All right, so this problem is from the 2008 exam, number 3. 2008 free response, number 3. So we have this wire here with a battery in it, okay? And they give us information about it. So I'm going to redraw this battery. The problem starts out by focusing on this loop of wire that has a battery. So I'm just going to redraw this right here. Now, what they tell us in the first sentence right here. So a rectangular loop of wire is connected across a power supply with an internal resistance. So if a problem talks about internal resistance, the way you think about that is it's like a little resistor that comes with the battery. Okay? It's a little resistor that comes with the battery. So the battery is 16 volts, and then this internal resistance is 0.5 ohms. So this whole thing right here is the battery. Now, what does the internal resistance do ultimately? What does the internal resistance of a battery do? Basically, what it does is it means that the total voltage of the battery is not going to be 16. It's going to be a little bit less, right? Because what happens when the current comes in through this resistor right here, through that internal resistance, what happens when current goes through a resistor? You lose a little bit of voltage. So the internal resistance just means that the total effective voltage is a little bit less. Now, what else do we have? We got the resistivity of the wire. So this goes back to chapter 17. The resistivity of this wire, 1.7 times 10 to the negative 8 ohm meter. So all materials have their own resistivity. And then let's see, the cross-sectional area. That's how fat it is. Not this area. We're not talking about that area. We're talking about, like, if you took this wire and cut it and then looked at it sideways like this, we're talking about how fat that wire is. There is an equation. There's an equation for the resistance of a wire. You know, if you just have like a long straight wire, the resistance of a wire equals resistivity L over A. Okay? So what they want us to figure out right here is the length of the wire used to make the loop. Now, the year that this was given, 2008, I'll bet you the number one mistake, and I'll be honest with you, I was solving, the first time I did this, I was in a hurry, and you want to know what I did? I fell into that mistake. Guess what I did? I took this resistance and I just plugged it in right there. Wrong. That's not correct. What we need to do before we use this equation, because we're going to use this equation, we're going to take this equation and solve for length, right? If you do the algebra, length is going to be resistance times area over the resistivity, right? We need to figure out the resistance of the wire. Now, they give us some more information. So when I was doing this in a hurry, I failed to note that they give us more information right here. When the power supply is turned on, the current in the wire is 4 amps, okay? I equals 4 amps. So if we use Ohm's law, delta V equals IR. R is delta V over I. So that's going to be 16 volts over resistance total. The total resistance of the whole thing, right? Wait. Oops. Back up. Over I. Amps, which is 4 amps. Sorry. This is resistance total. That's resistance total here. So the total resistance of the whole thing comes out to be 4 ohms. But look, this guy right here is what? That's the internal resistance of the battery. So you can kind of just think of it like this. Internal resistance of the battery plus the resistance of the wire equals resistance total. It's kind of like that. You know, the battery has its own resistance, and then the wire has resistance. The total resistance is going to be the resistance of the battery, the internal resistance, plus the resistance of the wire, right? So look, the internal resistance is 0.5 plus X equals 4, right? The total resistance is 4 ohms. So what must be the resistance of the wire? the resistance of the wire is 3.5. That's what gets plugged in over here, right? Not the 0.5. The 0.5 is the internal resistance of the battery. You guys follow that? Okay, so when you plug the numbers in, I'm going to let you guys plug the numbers in. You know, this is 3.5 ohms. The area is given right here. So plug in the area. The resistivity, you plug that in. You find out that the length of the wire is 0.72 meters. So that's a chapter 17 question. That goes back to chapter 17. All right, so I think that's it. Let's see. So yeah, calculate the length of the wire. That's how you do it. All right, let's go to the next screen. Yo. Well, now we're going to get to the magnet. Okay, so here. So now we got some more info here. So the wire loop is then used in an experiment to measure the strength. Okay, look, we have a magnet. We got a magnet, north end, south end. What do we know about magnetic fields? Like when we talked about bar magnets, you know, I showed you north, south. If you have a bar magnet, what does the magnetic field do? Comes out of the north like this, right? That's the magnetic field, and then loops around to the south, okay? Magnetic fields come out of north and go into south. So what is the magnetic field doing in this region right here? The magnetic field's going from north over to south, right? The magnetic field is shooting that way. Does that make sense? Okay, that's important. Okay, they tell us the length, so this segment of the wire, of that loop, this segment right here has a length of 0.02 meters. That's going to be important. Okay, let's see. The power supply is running, so 4 amps is the current in the direction shown. Okay, question B. Now, this involves right-hand rule number 1. In which direction is the force on the magnet? Well, the first thing we're going to do is find the direction of the force on this loop, right? And then we're going to use Newton's third law. What is Newton's third law? Every force creates a equal and opposite. So if we can find out the direction of the force on that loop, if we can find out the direction of the force on this loop, then the direction of the force on the magnet is going to be the other way. All right, which way is the force of the magnetic field on this current carrying loop? Okay, so it's 3-dimensional. So you're going to use right-hand rule number 1, flat hand rule. All right, which way is your thumb? Into the screen, right? Your thumb is pointing into the screen because that's where the current's going. See right there? The current goes into the screen. Which way are your 4 fingers? To the right. Why are my 4 fingers to the right? Because what's the magnetic field doing? The magnetic field shoots to the right. Okay? Which way is the palm of our hand? Down. So which way is the force on this loop of wire? Down. The magnetic field is pulling the loop down. So what must the loop be doing to the magnet? Pulling it up. That's kind of, you know. And if you look at the solution that the College Board gave, it's exactly that. It's like they want, you know, right-hand rule. You should have some sort of, you know, when you justify your answer, look at the solution that the College Board gave. They're looking for like right-hand rule, direction of force on the loop is up, and then Newton's third law, every force has an equal and opposite force. So the force on the magnet is, I'm confusing myself. The force on the loop is up. No, the force on the loop was down, so therefore the force on the magnet is up. Okay, part C. The reading on the balance changed by 0.06. Dudes, what is this 0.06 here? The reading on this balance, this is on a balance. It's like on a scale. What would that be? If the reading on the balance changes by 0.06, what are they telling us there? That's the force of the magnetic field, right? It's kind of like this. Look, if you're standing on a scale, right? Let's say you're standing on a scale. So like for me, I weigh about 200 pounds, right? if somebody ties a rope to me, right, and starts to pull me up with like, tension there. So let's say the scale, instead of reading 200 pounds, let's say it reads 180 now. Well, what must this tension be? 20 pounds. It's like that, right? So what they're telling us in this problem is the force of the magnetic field. This is the force of the magnetic field. This is FB. So that's 0.06 newtons. Now, there's an equation for force of a magnetic field. So we're focusing on this segment of the wire right there. There's an equation for force of a magnetic field on a wire. BIL sine theta, but the sine theta is just going to be 1, so we can solve for B. So you just go FB over IL, so that's 0.06 newtons over 4 amps, right? The current's given right there, 4 amps, and then L is this part right here. It's the length of this segment right there, 0.02 meters. So then this comes out as 0.75 Tesla. All right, next one. Okay, so here, check this out, dude. So here's the situation. Again, they're talking about the force on the wire. F equals BIL. And what they did is they made a graph like this. Force on the Y, length on the X. And look, I just want to point something out. Dudes, what's the equation for a straight line? I hope you know this. Watch, y equals mx plus b. So look, y equals mx plus b, right? The b is 0. That's the y-intercept. That goes to 0. Look at what's on the y-axis? Force. What's on the x-axis? Length. So what must the slope be? BI, dude. If you calculated the slope of this line, if you went, rise over run, what's the slope of this line going to be equal to? BI, right? BI. Okay, now, so that's the setup. All they did, force, length. No big surprise, guys. No big surprise. This gives a straight line. Now, what they say is this. On the graph above, sketch a possible relationship between the magnitude of the force on the magnet and the length of the wire segment if the wire segments were misaligned. So like if the loop is kind of like at an angle. Well, remember, this F equals BIL, there's one other part to the equation, which is what? BIL sine theta, right? So we're messing with theta here. So the magnetic field is going like this. It's going straight across like that, okay? What's going to happen to the force on the wire if you misalign it? So here's the B field. The B field is no longer perpendicular to the wire. What's going to happen to the force? Well, if the wire were like this, if the wire were parallel, that'd be sine of 0. And what's sine of 0? 0. If when the wire is like this, that's sine of 90, which is 1. That's a maximum. So what happens to the force when we kind of tilt the wire at an angle? The force gets smaller. So the answer to this question is just another line with a slightly smaller slope. That's the answer. That's all you got to show. It's another line. You're lowering the force. Okay. And then last one. Here we go. Last one. So here's our equation. F equals BIL sine theta. So look, suppose the loops are correctly placed perpendicular to the field and the following data are obtained. Describe a likely cause of this discrepancy. So what happens is it kind of goes like this. Now what could possibly cause this? You could pretty much make up anything that fits this equation. The most likely culprit would be B, right? I would say something like, the magnetic field is not constant, something like that. If the magnetic field were not constant, that could cause the force to drop off, something like that. Or maybe, I don't know, you could maybe say the current changes. the current, let's see, hold on. A likely cause. Yeah, like hey, you could say something like the resistance in the wire changes and the current changes. If the current changes, the force changes. I don't know. Don't say length. I don't think the length would change. All right, that's good.